Hello. If, like me, you have lots of these beads knocking around and wondering what the heck could I do with those, well, if you have some beads, some icy water and some near boiling water, you can incorporate this story, expand the story, probably better use of English, from your iodine, starch sensitivity. So there's one of our solutions, and you can see, well, I can certainly see from here, maybe if I hold it back there, it's a bluey, purpley, blacky colour. Well, not black, it's a bit of nice bluey colour. So I'm just going to pop that into the near boiling water, and we'll just, in fact, why not put 2 in? Because that's a slightly different one as well. Oh my goodness, can I see that already? Has that been 30 seconds or so? Has that noticed, but it has noticeably decolorized to me, but I'll leave it for another 30 seconds or so. So what are the beads for? I thought this was going to be a great use of my beads to model the starch, amylopectin and amylose model. So the single beads represent glucose, so single glucose units. The double disaccharide dimers represent maltose. As we know from our enzymic work, when we digest starch, we get maltose before glucose. Oh, I'll stop that story. This is far more important. So that was a minute and a half. It probably seemed longer listening to me, but those two solutions have totally decolorized. Going to pop them together into the ice bath while I continue the saga. In fact, it could be a nice way of proving, could it not, that enzymes work best at nearly boiling point, because your starch reaction has been about as good as it could be. Well, there you go. In no time at all, look, they're starting to colour back up again to be the bluey purple colour that first went in there. Just to show that it's not total fluke. I don't think it's total fluke. I'll put them back into there again and see if they decolorize once more, and then leave them in my ice cold solution. So what the heck is happening there? Clearly the starch is still there, it's just undetectable. Now what I had hoped, but then a degree of sanity prevailed, I was going to join hundreds and hundreds and hundreds of those beads together to make a big, long starch molecule. By the time you pressed half a dozen together, the novelty wears off, I can assure you. But oh, it's coloured up again, interlude, back to there again. I'm going to put that back into the cold water and just leave that do its stuff. So, a little bit of imagination. The starch molecule is long. In fact, cool, about as long as that. Not great, is it, for representing individual beads as being glucose units, but we get the idea, I think. So a starch molecule, amylose in particular, is a helical shape. Oh, come on, finger, a helical shape. So we've got a great big long, twisted helical shape. It's not doing very well, is it? But I'll hopefully get the idea. And the iodine molecules fit inside and cause a colour complex. I think if my pathetic biochemistry is anywhere near, that it's hydrogen bonds that hold that structure together, and as it gets heated up, then the hydrogen bonds pull apart. No, they don't. They're just not there, are they? So the molecule pulls apart, excuse me, and therefore the iodine comes out and decolorizes. As it all cools back down again, then the molecule of starch begins to coil back up, and the iodine is still in the solution, and then we have the colour complex happening again. Not the best piece of modelling using that lovely old bit of tape. So what we'll do in a moment is just have a look at a bit more realistic view of what a helix really looks like, and how those the differences between the starches of amylose and amylopectin. We might even wander into how the bonds are put together, 1,6 linkages, 1,4 linkages, but that's only if that appeals to you. But we'll look at that in a wee moment. But the important part is, there's my blue-black colour return again once it's cooled back down. So nice little novelty for your students.